In this video, we'll be looking at ways to calculate coefficient of viscosity. The first thing is viscous thing has to do with if I have say a layer of fluid and below that we have one more layer of fluid, and say if it tries to move, it will resist. It will resist the sliding basically. Okay, it will resist the sliding. This is nothing but your viscosity. Now, coefficient of viscosity, which is represented by eta. Okay, so if that was a person, say this was eta. If this was a person, it would be able to tell us, or he or she will be able to tell us. So if I ask eta, you know what can you tell us? What is your entire goal, or what is your expertise on? So eta is able to tell us how thick or sticky a fluid is when it flows. Okay, so that is the entire role of coefficient of viscosity. Okay, so in this video, we're looking at a way to figure it out, or a derivation of sorts. And we have a bunch of assumption, like pretty much all the derivations that we have done. Here too, we have assumption. So the coefficient of viscosity that we are calculating is fluids that are Newtonian. So what are Newtonian fluids? The fluids which follow a certain property. So that is rate of deformation is proportional to shear stress. Okay guys, if a fluid follows this particular relationship, it's said to be Newtonian. I can't go to the details of it, but this is what you guys have to keep in mind. And by the way, if you guys are not very familiar with stress, it is nothing but your tangential force per unit area. So basically, if I have, say, some whatever it is, if I apply a force in this manner, so those are your shear stress. Okay, so there is tangential force or your shear stress that is being applied on this object. That will eventually lead to object kind of bending this way. Okay guys, a fluid which is Newtonian, and the flow is steady and laminar. So these are all the conditions, consisting of parallel layers such that the velocity varies linearly with distance from the fixed surface. So this is the assumption that we are making. Right? I hope you guys understand the word laminar. Steady and laminar actually are interrelated. We're assuming that it consists of layers. By default, if you tell laminar, all of this comes into picture, such that the velocity varies linearly with the distance from the fixed surface. If you guys remember velocity gradient, it's talking about that. So from here, we're talking about velocity gradient. So I'll make it clear with this diagram. Okay guys, so this is basically what we're looking at. So I have a liquid layer, say this is of height L, and this area turns out to be A, and what else? So when we apply a force of, say, F, it deforms. It was like this, it became like this. And by the way guys, this is this second figure, figure 2. It is to do with your side view. So I'm standing over here and I'm watching this. So when I'm applying the force, I stood over here and I'm watching the fluid. Okay, so I get this picture. So an object which was liquid, which was like this basically. So technically, just a second. Oh, initially it was like this, and eventually, oh no, sorry, not that. It should be from here. Not good. Okay, yeah. A liquid which was over here, because of this force, a shear stress, it got deformed this way. So I have to measure this. I have to talk about this. I can talk about it with the help of angle dB. So it got moved by an angle of dB, and this length we'll consider it as dA, and the velocity at which this is a particle over here, the topmost layer, it's moving is v. Okay, and the particle over here, it's not at all moving, and so it's 0. So if we draw the velocity profile, I hope you guys remember velocity profile. This is 0 meter per second. The top one is v meter per second. Then if I happen to join this, right, and draw a line parallel to, well, this vector, I'll be able to figure out the velocity of a particle, say at a height of y. How? I can use similarity of triangles. So triangle O, if I call this as A and B, OAB is similar to triangle OA dash B dash, because they share one angle dB, and they are 90 and 90 over here. So these two triangles are similar, and with that in our hand, I'll be able to figure out the velocity over here. That will be equal to y by L, L being the entire length, y is this, times of v, velocity at the top. Okay, so this would be the velocity at any given height. This is a very simple, straightforward diagram. So I told you I'll come back to this. So what we're looking at is a Newtonian fluid, and it is flowing steadily and in the form of layers, and the flow is laminar. So no particle is crossing the path of other particle. It consists of parallel layers. So there are layers over here such that the velocity varies linearly. So you can see the velocity is varying linearly. Okay, so this line justifies that. So this is actually dotted line. Actually, no. Velocity gradient is we do draw it as solid, but yeah. Sorry, velocity profile. So point is, we are looking at a linear variation, as and when we move up, it will gradually linearly increase. So basically we are looking at an AP, so its starting value, A value is 0 and nth value is V. So at a position of Y, this will be the value per se. Okay, so wait, this is AP or GP? Linear, step by step if we go. So this is, this is an AP only. So this is our assumption. Okay, the diagram is clear. So this is step 1. Okay, now step 2. We are getting an expression for rate of deformation. So what we are trying to do is, we are trying to figure out the coefficient of viscosity. Coefficient of viscosity, it depends on, end of it depends on the friction, and friction occurs because of the force, and force is related to rate of deformation. So that's the whole idea. If the rate of deformation is less, means your coefficient of viscosity is high. If the rate of deformation is high, then the coefficient of viscosity is less. So we are trying to get an expression for rate of deformation and trying to go towards coefficient of viscosity. That's the whole plan. So now, rate of deformation. So what does it mean? Well, we are measuring rate of deformation with d beta, right? The angle over here, d beta. So d beta is proportional to tan d beta for d beta, the small value of d beta. So this is true for any value which is quite small. We can write this relationship. This comes from trigonometry. Since d beta is proportional to tan d beta, so d beta will be proportional to tan d beta. What is tan from this diagram? Tan is opposite by adjacent. Opposite is dA, adjacent is L. So it's proportional to dA by L. Okay. So what is dA? dA will be equal to V into t, velocity into time. So if I take time, this is 0 seconds. And this is t is equal to after dt, 0 plus dt. So the amount of movement seen over here will be nothing but product of speed into time. So displacement is equal to speed in time. So using that, so substituting dA, which is equal to velocity into time, we end up with d beta is equal to V times V by L dt. And therefore, rate of deformation is equal to V by L. So we got an expression for V by L. What is V by L though? V by L is nothing but velocity gradient. Velocity gradient. This we discussed in the very first video of this section. So next step is get another expression. Sorry, expression for velocity gradient. Okay. Now, how do you do that? See, from the figure, what do we have is, from figure, we understand that velocity at particular layer at height y is given by y by L times of V. Okay, we got it from the figure. Now, if I differentiate this, okay, so differentiating with respect to y, we end up with du by dy is equal to L and V are constant. So V by L times of differentiation of y with respect to y is 1. And V by L. So from 1 and 2, what can we conclude? So from 1 and 2, so from 1 and 2, we have du by, du, not dy, du by dy is equal to d beta by dt. So rate of change of angle with respect to time is equal to rate of change of velocity with respect to layers. That is commonsensical if you think about it. If I have this to be changing at a faster pace, then the angle will change at faster pace. Think about it. So let me show this actually. Actually, I had a video for you guys. I forgot. So if I have a block of solid like this, if I apply a tangential force, right, and say the bottom layer is fixed, so if I apply a tangential force, what will happen to the surface or the object? It will shear like this, it will move like this. If I take a book and if I hold the bottom and if I apply a force, right, brushing through the topmost surface, the object will shift to this, is it not? The rate at which this angle is formed, the rate at which the angle is changing for this line is dependent on the velocity. Of course, indirectly dependent on the force. That's what we're going towards, right? And that's what the result is about. So I just write for the sake of understanding. Rate of change of velocity. Okay, let me change of velocity with respect to layers or length, not layers, sorry. With respect to height or length, whatever you guys want to call it as. It's related to rate of change of angle with respect to time. Okay, now final, we have step 4 if I'm right. As per our assumption, since the fluid is Newtonian, we have your shear stress is equal to rate of change of angle, deformation basically. So from here, what can we do? We can call this as 3, substituting 3 and here we have du by dy. Sorry, proportion, my bad. This is proportion not equals to proportional to. So basically, when I remove the proportionality, I'll get a proportionality constant, and that is nothing but your coefficient of viscosity. And now let's substitute force per unit area is your force by area is your coefficient of viscosity times of du by dy. So this is one expression. There are many possibilities, but this is one of it. So now, if I happen to, I don't have space. If I happen to substitute A as 1 and the rate of change of, and what else, du by dy or your velocity gradient as 1. If you consider this, right? If I do this, what happens? This is 1, this is 1. So then I'll get nu is equal to F in terms of magnitude. Remember, we are trying to figure out your coefficient of viscosity. Sorry, I keep calling this as nu. Eta is equal to F. So what does it actually mean? Eta is equal to F. So with this conclusion, let me write a statement. Let me write it from here actually. I don't have space. Hence, coefficient of viscosity eta of a liquid may be defined as, can be calculated as. So viscosity can be found. So that's what we are trying to do, right? Can be found by finding the tangential force per unit area. I'll change the color so that per unit area required to maintain a unit velocity gradient between two fluid layers. Okay. Sorry, till now I might not have made a lot of sense. So what we are trying to do here is figure out the value of, say I gave you guys a liquid, some gooey material. I ask you guys to, figure out the coefficient of viscosity for this. So what you guys will do is, you will say take a structure which is of this form, and you will put the liquid into it, for example. Then you will apply a force such that the velocity gradient, okay, I hope you guys understand velocity gradient. So the velocity gradient turns out to be 1. So 1 per second. I hope you guys remember. So for a meter length, if this is 1 meter length, if this is 1 meter long, if this is at 0, this should be moving at 1 meter per second. If you are able to do that, and if you got some value of F for that, say 10 Newton, if I'm applying 10 Newton of force, and if I'm able to see a velocity gradient of 1 per second, means your coefficient of viscosity is 10. Okay, so let me again explain it with a bunch of diagram and stuff. Say I have a meter long liquid, whatever liquid I gave, and then, sorry, not L, 1 meter long, and say you guys applied, say 12.4 Newton of force, and once you applied that, you got to see that if this is 0, the topmost layer over here is moving at 1 meter per second. Then your coefficient of viscosity in terms of magnitude will be equal to 12.4. I'm not writing the SI unit, some unit. Okay guys, so that's how we'll be able to figure out the point is we need to figure out the coefficient of viscosity. How is that we are doing? We are taking up 1 meter long of that liquid. We are applying a shear force, shear stress, tangential force. When you apply the tangential force, we got to see that the topmost layer is moving at 1 meter per second. If this happens, then that particular force value, numerical value, will give you guys the coefficient of viscosity. Again, you need to imagine this, right? You had something like this initially, a liquid which is of this structure. Then you applied a tangential force. When you applied that, what happened? It got sheared. It deformed in this manner. And the rate at which it's deforming is, say, so the velocity gradient turns out to be 1 meter per 1 second, actually 1 meter per second per meter. So for every meter of height, the rate at which the liquid is going forward turns out to be 1 meter. Okay, so that's the difference. So this particle and this particle have a difference of 1 unit along the x-axis. I don't know how much sense I made it to you guys over here. So this is at, say, 0, 0. This would be at 1, 1. Okay, I'm trying to tell you guys in many different ways. I hope you are able to figure it out. So that's what the entire derivation is telling us. If you guys don't want to understand this, if we just want to look at the derivation, it's quite simple. So we need to make some assumptions and then draw a diagram, right? And figure out the velocity gradient. Get an expression for deform using simple trigonometric ratios. And we will get another expression for velocity gradient, again using the diagram or the velocity, actually diagram itself, using similarity of triangles, using A similarity of triangles. Okay, this is actually from Sorry, I can't write it over there. Yeah. This is with AA similarity of triangles. We got this differentiated. I got one more expression for V by L. So I'm able to figure out your stress, tangential stress, using this particular expression. So since we got this expression, we equated all the values like A and velocity gradient to 1. When we did that, the force numerically turns out to be equal to the coefficient of viscosity. And that's how we'll be able to figure out the coefficient of viscosity. That is the agenda. What does it mean physically? I try to explain that. Okay, so I hope you guys got a gist of what I'm trying to tell, because again, honestly, if you have understood all the things before this, there are a lot of concept. I had told in the very first set of videos of the very first set of chapters, I have kept telling you guys that everything keeps on adding now onwards. How 1 plus 1 is a commonsensical answer to you guys. Every term that I'm using over here, stress, tangential force, gradient, all of this has to be a second nature to you. Maths has to be very strong. Mathematically, if you're strong, whatever I'm writing on the screen should just pop up to you, It should animate in front of your eyes. All of this should be, you should be able to visualize it. If not, your fundamentals are weak. That's what you need to work on. If it's not making sense, your fundamentals are weak. That's the hard truth. Okay. You can pause and have a look.